Hello dear student, myself Dr. Sarika Kalra, Associate Professor in Electrical Engineering Department from Ajay Kumar Garg Engineering College. I will be taking your electrical machine 1 subject. In this there is a 4 module. In module 1 the single phase transformer, module 2 3 phase transformer, module 3 is the electromechanical energy conversion, and in module 4 and 5 include the DC machines. So, in this lecture I am discuss about the transformer, what is the importance of the transformer, and after that we will see the basic laws and the basic magnetic law and the magnetic circuit, because these basic magnetic circuits are very important to understand the transformer basics. So, these are the content of my lecture. First is the basic magnetic law, then magnetic circuit with the DC voltage, magnetic circuit with the AC voltage, and then BH curve and the concept of magnetizing current. So, before going this content, first we see why we use the transformer and what is transformer. Transformer is the static device that is used to transform the energy from one electrical circuit to the another electrical circuit through a magnetic medium without changing the frequency, and it is based on the principle of electromagnetic mutual inductance. Third, the transformer function is to change the level of voltage or current. Either you can increase the voltage of level or you can lowering the voltage or level. So, and one question in my mind, why you use, where you use this transformer? Because there is many application in transformer. The main application of the transformer is in power system, like when the power is generated at the generating end through a alternator, it is a 3 phase voltage. So, the generation is restricted because the construction is restricted with the alternator. So, if you want to transfer this voltage to the receiving end, you have to increase the voltage level. So, if you want to increase the voltage level, that voltage level you can increase by the transformer, because if you transmit the voltage at a higher level, the transmission losses will be reduced. So, this is the main function of the transformer. Second, it can be used for the impedance matching for maximum power transformer in electronic circuits. Third, it can be provide the isolation between the two circuits. So, in the next coming lecture we will see the transformer concept and the magnetizing current, the phasor diagram and all the equivalent circuit. But before going this transformer, in this lecture we will going the basic concepts of the magnetic law and the magnetic circuits. These are the basic laws: the Faraday's law of electromagnetic induction, second is the Lenz's law, then laws of electromagnetic forces. In this there is a Fleming's left hand rule, Fleming's right hand rule and the Ampere circular law. So, the Faraday's law is whenever there is a flux, there is a change in flux, the EMF is induced in the circuit, and that can be represented by, sorry, so this is the Faraday's law. When there is a change in flux, the EMF is induced in the circuit, and this is the number of turns of the coil. Okay. This negative sign represent the Lenz's law. This negative sign represent that whenever there is a changing in flux, the polarity of the EMF is induced in such a way that it will oppose the flux, oppose the cause of production. Okay. So, this is the Faraday's law, and this is the negative sign represent the Lenz's law. So, next is the Fleming's right hand rule. So, in Fleming's right hand rule, so this is apply only for generators. Okay. So, in this Fleming's right hand rule, if you see this finger represent like this, if the thumb represent the direction of the rotation, the forefinger represent the direction of the magnetic field, then your middle finger will be represent the direction of the current of the generator. So, by using this Fleming's right hand rule, you will find the direction of the current in the generator. So, if it is thumb, that is direction of the rotation, this is suppose forefinger, that represent the direction of magnetic field, this will represent the direction of current. So, this is how you will find the direction of the current in the generator. This is third rule and this is fourth, that is Fleming's left hand rule. So, this is apply on the motors only. So, this is left hand rule. So, you just put the fingers like this. If the direction of the magnetic field is represent the forefinger, direction of the current represent this middle finger represent the direction of the current. So, the thumb represent the direction of the rotation of the motor. Okay. And put this all these finger and thumb like this, that means it is 90° from each of this. Okay. So, if this is thumb, this is middle finger, so if the middle finger represent the direction of current and this forefinger represent the direction of magnetic field, this thumb represent the direction of rotation of the motor, direction of Okay. So, this is the Fleming right hand rule and left hand rule. Next, we will see the Ampere circuital law. This represent by this implies when the magnetic field intensity is in a closed path is equal to the current enclosed by that path. So, if there is a current, we will find the magnetic field. Okay. So, this represent the by the right hand. So, if the direction of the current is upward, you will find the magnetic field direction which is in anti-clockwise. If the direction of the current is downward, you will see the direction of the magnetic field is clockwise. Okay. So, this is how the Ampere circuital law will represent. In this, we will see that the integral of magnetic field intensity is closed path is equal to the current enclosed by that path. Okay. So, now we will see, now we see that these are the basic law. Now, we see the magnetic circuits which useful to study the basic principle of the transformer. So, I am just first considering the magnetic circuit with the DC voltage. Okay. So, I have taken a core, this is the core which have the some permeability, and we apply one coil is in this core is there, and we apply the I apply this DC voltage. Okay. So, according to the Ampere circuital rule, when you apply the DC voltage, the current is flowing through the coil that represent the, this is equal to the current. When you apply the DC voltage, the current will start flowing and it is flow through the core of the magnetic circuit. So, this can be represented by the this H is the magnetic intensity, dl is the mean length, and I is the current which is flowing in the circuit. Okay. So, it can be represented by this dot product I. Okay. And this H, if okay, suppose the coil has the n number of turns. So, the total current enclosed by the coil is Ni. So, it can be written as Ni, okay, where L is the mean length of the core. So, H is equal to Ni by L. Okay. As you know that the flux density represents B is equal to mu H. As this is you already know, the B is the flux density, mu is the permeability of the material, that can be represented by this mu is equal to mu 0 and mu r, where mu 0 is the permeability of air gap permeability and mu r is the relative permeability. Okay. So, this, suppose this is the equation 1, right. So, this H value you can put in this equation 2. Okay. So, in the next slide, B is equal to mu, H is equal to, that is N I divided by L. Okay. And you already know the expression like phi is equal to B A, where A is the, phi is the flux, B is the magnetic flux density, and A is the area of the cross section area of the core. So, if A is the so phi is equal to B A. So, put this value of B from equation 3 in equation 4. So, phi represents mu N I divided by L A. Okay. And this can be written as L by A. Okay. This N I divided by 1 upon mu 0 mu r L by A, as mu 0 is equal to mu 0 into mu r. Okay. So, now this we can see the flux is equal to N I divided by this 1 upon mu 0 mu r into L by A. So, this is called the reluctance. It can be represented as N I by R, where R is the reluctance, and it can be equal to 1 upon mu 0 mu r into L by A. So, this R is the reluctance. Okay. That means, and this N I is the called the MMF. Okay. So, this MMF is the cause by which we can produce the flux. So, this MMF is the cause, and due to this cause, the cause of this MMF is the phi is the effect of this cause. Okay. So, in DC circuit, when you apply the voltage, the current will start flowing, and this current is responsible to produce the flux in the core. Okay. And this circuit you can analogous to the electrical circuit, like this can be analogous to represent by like electrical circuit, as electrical circuit is the current is equal to EMF upon the resistance. That means, the current is in electrical circuit is analogous to the flux of the magnetic circuit, and this EMF is analogous to the MMF of the magnetic circuit, and this reluctance is analogous to the resistance of the magnetic circuit. Okay. So, in DC circuit, this is in the magnetic DC circuit, magnetic circuit of when you apply this DC voltage in the magnetic circuit, the flux is responsible, the current is responsible to produce the flux. So, that this Ni is the MMF which produce the flux. So, the cause of the MMF, what is the cause of this MMF? The effect, and the effect is your flux. Okay. Now, we discuss the magnetic circuit with the AC supply. Here is the AC supply, this is not the DC. So, in AC circuit, when you apply the voltage, I have considered the magnetic core with only one coil with the AC voltage. So, when you apply the AC voltage, the current will start flowing, and this current is in sinusoidal in nature. Suppose this is IT, this represent I am sin omega t. You can take cos omega t, whatever you like in sinusoidal, like if you want to take cos omega t, or you all also take the sin omega t, it depends upon your convenience. Okay. So, the flux represent the okay. So, this voltage is in changing in nature. So, according to the Faraday's law, the EMF is induced and the value of this EMF is equal to minus N d phi by dt. Okay. So, put the value of phi d phi by dt, where the phi is phi m sin omega t. So, it can be written as n phi omega cos omega t. Okay. Just see. So, that means this represent the maximum value of voltage. Okay. So, E max is equal to minus N phi m, or we only consider the magnitude. Okay. Negative sign only represent the Lenz's law. Okay. So, what is the value of RMS voltage? E max by root 2, and this can be represented by root 2. So, in this ERMS, put the value of omega pi f phi m n divided by root 2. So, it can be represented by 4.44 f phi m n, that is ERMS. That is induced voltage in the coil. If the magnetic circuit contain one coil, this EMF is induced in the coil. Okay. So, you see that this is the magnetic circuit with the AC supply, and here the EMF is induced, right, and the polarity in such a way, so that it follow the KVL. That means, this E must be equal to the supply voltage must be equal to the EMF. Okay. Must be satisfied the kVA. Obviously, it must be satisfied by the kVA in magnetic circuit. So, this V must be equal to this EMF induced. So, it can be written as this V is equal to ERMS, and that can be 4.44 F phi m n. This is V. So, phi m can be represented by V upon 4.44 F multiplied by n. Okay. That means the phi maximum value of the flux is depend upon only the supply voltage and the frequency. As you apply the voltage, your flux is fixed within the core. The maximum value of flux is fixed within the core. Okay. But it is not in case of DC circuit. Okay. So, now we will discuss the concept of magnetizing current. We will see that BH curve, how this BH curve behave, and from this we come out the concept of magnetizing current. Okay. So, you will see that this BH curve, the BH curve is the BH curve between the three material. Now, suppose in AC circuit you have applied this voltage and this phi max will be fixed as you apply the voltage, because it depends upon the voltage and the frequency of the supply, right. So, if your phi max is fixed, B max, what about B max? B max is equal to phi max upon A, or you can say phi is equal to B max multiplied by A. A is the cross section area of the material, of the core. So, if your phi max is fixed, your B max is also fixed. So, from the BH curve, suppose this is phi max for this material, for this. So, corresponding this B max from cast iron material, your H, the flux intensity is somewhere around here, like this. Suppose it is H1, H max 1, right. Now, and this H max is proportional to the current. So, you can say H max is equal to I max 1. Okay. And the same Bx for the cast steel material, the H2 become this, H2 max is like this, and it is this. So, H2 max is similar to, you can say, this I2 max, because H2 max, what is H2 max, or H is equal to Ni by L. So, N is fixed, L is fixed. So, the H max, you can say that this is proportional to the current itself. And for this Bx max, for this sheet steel material, it can now more reduced. This is I 3 max. So, from here you can see for the constant flux, max value of flux, as you increase the permeability of the material, the requirement of the current will be reduced, and this current is called the magnetizing current. Okay. So, as you increase the permeability, suppose you have the very good material, like which have the permeability is like tends to infinite. So, your the magnetizing current, the requirement of current which will produce the total amount of flux is reduced. Okay. So, if your permeability is like tends to infinite, your the magnetizing current will tends to 0. Okay. Because this magnetizing current concept is come in this transformer. So, it is very important to understand this. Okay. So, for the same flux production, the B max is fixed, but according to the material, because these 3 material have the different permeability. Okay. So, according to that, as this increase the permeability, because sheet steel permeability is greater than the, suppose its permeability is mu 1, this is mu 2 and this is mu 3. So, mu 1 is greater than mu 2 is greater than mu 3, and as the permeability will increase, this I max suppose this is 2, just a second. Suppose this is 3, 2 and 1. So, mu 3 permeability is higher than this mu 2 and this mu 2 is greater than mu 1. So, this represent that I max 3 is less than I max 2 and is less than I x 1, and this I max is the magnetizing current. Okay. So, this is the basic of the material property, like the requirement of the magnetizing current will reduce by choosing the higher permeability of the material for the production of the constant flux. Okay. I already explained this BH curve. These are some relative permeability of the material by which you can choose the which kind of material you are using to build the transformer. Okay. Thank you.